Today we're going to start review for the final exam and finish it up on Thursday. I'm pretty sure I won't be able to get through all of it in one sitting. But since the final is going to be available, and in fact, Grace, you're the only one that's required to take the final. Everybody else tested out. They all have A's in their exams. So this is for your benefit and the benefit of posterity. And I've got a review document up on the screen with the answers in it. I can't recall, I put it together so quick, I can't recall if I put it on Brightspace or not. But everything's here. All right, is there any business or questions or anything we need to deal with before I get started? If not, let me see if this thing's going to work, if it'll page for me. Okay. That's a little bit good. All right, so the way this is set up, I'm going to do every one that's in the document. This is not a case where I have the review documents handed out and I pick out certain ones and do the whole thing, because every question is unique. All right, so number one. Which of the following is an example of a quantitative observation? Remember the difference between quantitative and qualitative. Actually, the definitions are almost in the word themselves. This describes a quality, something that's not, you can't quantify it. Quantity means amount, numbers, whereas qualitative is just a descriptive term. So the one of these that works, you can see that the, let's see, a piece of metal is longer than a piece of wood is qualitative. Solution one is darker, qualitative. The liquid in the beaker A is blue, that's qualitative. The temperature of the liquid is 60 degrees Celsius. That's a dead giveaway when you've got actual data, that is numbers, to go along with a statement. So D would be the answer for one. All right, let me see if I can scroll this one. No, I think I'm going to have to do some of these manually. There we go. Number two. Which of the following figures represents results have high precision? Remember the difference between precision and accuracy. Accuracy is how close is the value to the accepted value. I say accepted because it's almost impossible to find what we would call a true value. So accepted value is more commonly what you'll find. But precision has to do with grouping. High precision is close grouping. So close grouping here would be both 2 and 3. You got a grouping there, you got a grouping there. This is also precise. This one, this is also accurate, excuse me, accurate and precise. This one is not accurate and precise. And this is neither. right? So 2 and 3 satisfy the conditions, which would be E. All right, let's see. Page down. Yeah, 3. These first ones ought to go pretty quick. The amount of uncertainty in a measured quantity is determined by 2 factors. Every measurement has uncertainty. Every measurement. So, what we're talking about is what factors can we control? Or what factors do we have to account for? Sometimes you can't control the factors. One of them is the operator. Who's doing the measuring? And the other is equipment. So both the skill of the observer, the operator, and limitations of the instruments, the equipment. That's why A is the best answer for that. All right, number 4. 4. I think these problems are going to be pretty much in order that they occur in the textbook. The boiling water is what? Well, if we look at the answers, we see what the question is asking has to do with physical versus chemical change. The boiling water is a physical change for one reason. Liquid water versus vapor, you've still got water. The identity of the substance has not changed. That's a physical change. And it's not because the water just disappears here. The physical change because the gaseous water is chemically the same as the liquid. That's the key. Identity. I think I'm going to need a new marker. So I might as well get one before that one runs out. All right. Looks like we can get, let's see, 5 and 6 on the board. A solution is also called what? This has to do with definitions of mixtures. A mixture is a combination of 2 or more substances that retain their identity while they're in proximity to one another in the mixture. And there's no chemical reaction. So you can also subdivide these into either homogeneous or heterogeneous. And that has to do with the sampling composition. If you sample that mixture anywhere in the mixture, and every time you sample it, you get the same exact percent of each of your components, that is a homogeneous mixture. Homogeneous mixtures are also called solution. So that answers the question. Let's see, that green doesn't show up too well. Let me use the pointer. Homogeneous mixture is also a solution. That's why the answer is A. Number 6. Which of the following has a different value on the moon compared to the Earth? Well, we look at our choices, right? We have mass, We have time. We have weight. And we have moles. And we have none. Okay, so we're looking which one has a different value on the moon than it does on the Earth. Where's the difference? Mass is the same everywhere in the universe, except under extreme conditions. Sometimes we refer to rest mass versus relativistic mass, but we're talking about under most circumstances. And in fact, between the Earth and the moon, those are Newtonian situations, we call them. Mass is going to be the same no matter where you are, because it's a measure of substance. How much substance is there? So mass is not. How about time? Same problem. If you get yourself into a relativistic situation, like near a black hole, then, or you start traveling closer to the speed of light, then time changes. But between the Earth and the moon, time's the same. How about weight? Weight is an expression of a force. And the force is due to the presence of masses of different sizes and proximities, right? So the closer they are together, the greater the force, the greater the weight. The bigger they are, the greater the weight, the greater the force, the gravitational force. That's what we're talking about here. And that will be different on the moon, because the moon is about 1/6 the mass of the Earth. So its gravitational attraction will be about 1/6. Right? Moles is an expression of numbers of things. That doesn't change no matter where you go. So C is the answer. All right, let's see if I can page up to get this one. There we go. Almost got 3. So that's 7. All of the following are true, except that this is a cautionary tale. Watch the wording. When you read a question, pay attention to the wording. If you don't, then you might say, all of the following are true. We're looking for the exception. Okay. A, ions are formed by adding electrons to a neutral atom. That's not the only way you form ions, but as far as that statement goes, it's true. You can add electrons to a neutral atom and make an ion. It'll be a negative ion. It'll be an anion. That is true. Right. B, ions are formed by changing the number of protons in an atom's nucleus. That one is patently false. What happens when you change the number of protons? You don't have the same element anymore. You cannot form the ion of an element by changing the protons. You may form an ion of a different element, but you won't form an ion of the element you started with. So B is false, and we found our answer. And since there are no oddballs in there, like none of the above, 2 of the above, and all that stuff, once you find your answer, you can stop. And that one is false. Okay, so B is the false one here. How about 8? All of the following are characteristic of metals, except, there's another except. All of the following are characteristic of metals except. Are metals good conductors of heat? Yep, definitely. Are they malleable? Yep. Pure metals are malleable. That is, they can be squished and formed. Are they ductile? Ductile means, can they be stretched into thin wires? Yes, they can. How about D? They're often lustrous. Notice the qualifier there, often. They're often lustrous, and many times you have to have a solid piece that's been polished before you can see the luster. If you have a metal that's formed by a chemical reaction, sometimes the particles are really small and they actually look black. Silver is a good example of that. But once you build up enough silver in a layer, you start to see the luster. So they often are lustrous, yes. And E, tend to gain electrons in chemical reactions. Do metals gain electrons in chemical reactions? No, they do not tend to do that. They can be forced to do that, but they don't tend to do that. Metals tend to lose electrons. And form cations. So E is the false one. All right, I'm going to have to scroll number 9 just a tad. Yeah, let's see. There we go. Number 9. Which of the following is paired incorrectly? Right. So we've got a pairing of chemical formula and whether or not is it strong acid, strong base, weak base. Right. Those are your choices. So which one of these is not paired correctly? Is A correct? Strong acid, H2SO4. What is H2SO4? That's sulfuric acid. Yes, that one's paired correctly. How about HNO3 and weak acid? No, HNO3 is nitric acid. It is a strong acid, chemically speaking. Remember, a strong acid, this is an aqueous solution. When it ionizes, like that, right? Aqueous solution. Virtually all of it goes to this side. None of that's left. That is a strong acid in chemical terms. So B is the one that's not paired correctly. Barium hydroxide is a strong base. Hydrochloric acid is a strong acid. And NH3, ammonia, is a weak base. Remember, and this is in terms of the Bronsted-Lowry acid-base definition. This is a weak base. Why? Because when it hydrolyzes with water, it picks up a proton and leaves behind a hydroxyl, but the equilibrium here is way, way over here. It doesn't want a proton, maybe a few of them, but not many. That makes it a weak base. It's a weak proton acceptor. That's a weak base. All right. Let's see. 10. Which of the following are incorrectly paired? Here we go again. All right. Is this one paired correctly with its name? Yes. That's the small Greek letter lambda, which stands for wavelength. That's true. How about this one? Frequency and the small letter nu. That is paired correctly also. How about C? The little c can mean many things, but in this context, C stands for the speed of light. For instance, Einstein's equation, that's the speed of light. How about D? Hertz. hertz in the units of measure of hertz are reciprocal seconds. In other words, 1 hertz is 1 complete wave passing a fixed point every second. That's 1 hertz. And it's often abbreviated like that. But when you're using it in a calculation, very often you need that reciprocal second. And then E, X-rays, shortest wavelength. X-ray. Short wavelength? No. Short. Frequency? Yes. Very short frequency. Remember, excuse me. Wait a minute. Hold everything. Incorrectly paired. Okay. Yes, this is true. Short wavelength, but not the shortest. What has a shorter wavelength than X-rays? Gamma rays. Gamma rays are a much shorter wavelength, which means much higher energy. So E is the incorrectly paired one. All right. Scroll that one a little bit. Okay. 11. Oops. What did I do? There we go. 11. Consider the following portion of the energy level diagram for hydrogen. So these are actual energy values for the principal quantum numbers N1 through N4. And remember, the smaller the number, the more negative it is, because high energy is more positive. So further away from the nucleus is higher energy, which would be the more positive value. See, that's less negative than this one, and then from this one, this one. The most negative is N1. That's the lowest energy, which means it's in terms of how much energy has to go in to move that electron to infinity. Okay, the question is, which one of the following transitions does the light emitted have the longest wavelength? The longest wavelength. Longest wavelength means the smallest frequency and the smallest energy. So when you're talking about an electron transition around an atom, the shortest transition is the lowest energy. The shortest distance between levels is the lowest energy, which would be the longest wavelength. So if we look, sometimes it helps to draw a picture. If we look at the nucleus here, and we got 1 proton, and then we have a level here that's n equals 1, and then we have a level here that's n equals 2, and then 3, and then 4. Notice as you get farther from the nucleus, the energy levels get closer together. So if an electron jumps from 4 to 3 versus 4 to 2 versus 4 to 1 versus 3 to 2 versus 2 to 1. Which one is the shortest jump? That will give you the longest wavelength because it's the lowest energy. It's this one right here. 4 to 3, which would be A. Okay. That's number 11. I have to scroll for 12. And I got 13 on there also. Number 12. Which of the following statements best describes the Heisenberg uncertainty principle? Remember, the Heisenberg uncertainty principle basically says that you cannot know both where an electron is and how fast it's moving. In other words, you cannot know its energy. Technically speaking, you can't know its momentum and its position with any degree of accuracy, both at the same time. If you nail down one of them, then the other one has too much variability. You can't fix it. So which one of these statements says that? Well, the exact position of an electron is always uncertain. No, you can find it. You just lose that momentum term. It gets too big. The velocity of a particle can only be estimated. No, you can estimate the velocity. You just don't know where it is. You know how fast it's going, but you can't find it. C, it's impossible to accurately know both the exact location and the momentum of a particle. That's the winner, C. That is Heisenberg's uncertainty principle in words. There's a formula that goes along with it, but I'm not going to bore you with that again. We got that during the lecture. Okay, so this one's C. About 13. Which of the following is an incorrect designation for an atomic orbital? Okay. A, B, C, D, E. Now we're talking about electron configurations. 1s. Is that true? Yeah. Principal quantum number n can have how many here? Start with 0 and work your way up to n-1. That's it. All right. And remember the L's, that one's an S. How about B? 3D. Okay, 3D. So we have 3 here. We can have 0, 1, and 2. Right? 0, 1, 2, 3. 3 orbitals, 1 orbital, 3 orbitals. So, and this one's called an S, and this one's a P, and this one's a D. So that one's good. Those two are good. How about C? 1 P. Nope. If you have n equals 1, you only have access to S. P's and D's are out. So that one is false. And we found it. We found our answer. It's C. All right, let's see. Yeah, there's 14 and 15. Okay, which of the following was not an elemental property usually predicted by Mendeleev for unknown elements? Mendeleev did predict the existence of several elements and left positions in his periodic table, empty spots, to be filled by those future elements. But there are certain things that he could predict about them and certain things he couldn't because of the state of knowledge at that time. So, which of the following was not a property? Electron configuration? Yeah, they knew nothing about the structure of the atom. They didn't know about electrons. It wouldn't be long, but they didn't know about them then. What they did know, thanks to Avogadro and his student Cannizzaro, was how to measure the masses of individual atoms or groups of atoms. And that helped Mendeleev construct his table. In fact, he puts it in writing. I can't recall if it was in a referee journal publication or if it was in correspondence between himself and other scientists. But he did give Cannizzaro and Avogadro credit for helping him construct this table by their discoveries in Cannizzaro's publication. So they did know atomic mass, thanks to Cannizzaro's work. They definitely knew density. They knew boiling point, that was easy. And oxide formula. Oxide formula was something that we didn't discuss in great detail in class, but anything that's combined with an oxide, and you'll have so many of them, that's the way many elements were isolated. They were essentially combusted in oxygen, and that separated them into different compounds that could be easily divided from one another. And these compounds were called calx. That's where we get the term chalcogens for all the members of the oxygen group. All right, 14. That first one was the wrong one. 15. Which of the following atoms has 3 electrons in p orbitals in its valence shell? We need 3 electrons in p orbitals. This is where you need the periodic table, because the periodic table is constructed to tell you where the valence electrons are. That's one of the things that it can do. Here we go. So I got my periodic table here, and we're going to look at these elements, A, B, C, D. We got barium, gallium, vanadium, and bismuth. Which of the following has 3 electrons? 3 electrons in its p orbitals. All right, so what you need to do is to use your periodic table, and you know where the p orbitals are being filled in this part of the representative elements over on this side. So when you get to the first one in that group, the borons, there's only 1 p electron. Next door, carbon has 2 p electrons. And then the nitrogen group has 3 p electrons. So let's see, is there anybody in there that's in the nitrogen group? Let's see, barium, no. Gallium only has 1 electron in the p group. Vanadium's a transition metal. Now, we have to take some liberties with this question. Which of the following atoms has 3 electrons in p orbitals in its valence shell? That is, its outermost shell, right? It may have p electrons in the core, but we're not interested in those. We're interested in the valence shell. So, how about bismuth? Yeah, as it turns out, I'm going to come closer. Bismuth is right here. 1, 2, 3 to the right. It has 3 valence electrons in its p orbitals. Right there. All right, let's see. I'm going to scroll a little bit. Yeah. Let's do it this way. There we go. 16. Recording. The force between two bodies having identical electric charge. The force between two bodies having identical electric charge. That means both positive or both negative. Is a force of repulsion. Yep. They repel. We found our answer. This one says force of repulsion if the charges are negative and one of attraction is positive. Nah, I don't think so. Like charges repel, no matter what they are. Increases as the bodies are moved further apart? No. Decreases with distance. That's Faraday's law. Is independent of the distance between them? Nope, sorry. Directly proportional to the distance between them. Actually, it's inversely proportional to the square of the distance. So if I'm a positive particle and there's another positive particle right here, if this distance is 1 and then that particle moves 2 away from me, now the force is only 1/4 of what it was. Double the distance, force is cut by 1/4. Okay, so A is the right answer. They repel one another. Why is that important to chemistry? I mean, it looks like we're talking physics. Well, as a physicist would say, chemistry is just applied physics. And much of chemistry can be explained through electrostatic interactions. In other words, interactions of charges. Not all, but a lot of it can. Okay, so let's 16, 17, here we go. Which of the following has 61 neutrons, 61 neutrons, 47 protons, right, and 46 electrons? All right. So of the ones that we can choose from, is this going to be neutral or charged? 47 positives, 46 negatives, it's going to have a charge. What's its charge? It's going to have a positive charge. One positive more than the negatives makes it +1. So whatever it is, it's going to have 1 plus charge. Now, since we're given in this format, we're given the number of protons, the Z number, the atomic number. All we need to look for is 47. So which one has 47 and a single charge? Oops. This one right here. Come on. There we go. Silver. With 47 protons and 108 nucleons, summation of these two. Let's see, is that right? 7 plus 1 is 8, 4 plus 6 is 10. Yep, that's the one. B is the answer. Let's see, 118. I gotta scroll just a tad. There we go. 18. All of the following are in aqueous solution, which is incorrectly named. Notice that we had to say they were in aqueous solution because all of them have protons here, proton here, 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 here. That means that those, the way we write these formulas, those protons are available to be ionized. They can be taken apart and added to water to make the water acidic. But all of these are acids. What we need is the acid naming convention, and to do that, they have to be in an aqueous solution. Okay, so which is incorrectly named, right? is H2SO4 sulfuric acid. Yeah. It has an oxygen in it, so you don't say hydro to begin with. You just take the polyatomic on the end, sulfate, H become X, sulfuric acid. That one's correct. How about H2CO3? Right? Oxygen, so we don't say hydro. We look at this part. That is the carbonate. Polyatomic ion, H become X. This is carbonic acid. That's correct. How about this one? H3PO4. That's the phosphate ion. H become X, phosphoric. We sort of modify a little bit so it sounds better. Phosphoric acid. That one's correct also. How about HCN? There's no oxygen in that molecule, which means you have to start with hydro. Hydro. And then what this is, cyanic. Because it's derived from cyanide, IDE becomes IC. Hydrocyanic. That one is wrong. And the last one is correct. So D is the wrong one. That's incorrectly named. All right. Oops, gonna have to scroll a little bit. I made a drawing for this one, it looks like. Yeah, I think we can get enough of that in there to see what the question is. A manometer is attached. Oh, I got it covered up. That's a problem. Let me see if I can figure this one out. No. Hold on a second. No, it's not going to let me move it. Wait it. Nope. All right. Maybe we can deduce what the question is from the drawing. Here's our manometer. The manometer has a volume of 2.34 liters in this trapped gas. The manometer measures the pressure inside that vessel. So we have 1 atmosphere bearing down there, or whatever the pressure happens to be. Let's see, 1.23 atmospheres. Yeah, 1.23 atmospheres out here. Okay. And the difference between this level of mercury and that level of mercury is 24.3 torr. That's the difference right here. Okay. What is the actual pressure inside this vessel? What is the pressure of that gas? Well, notice that you've got pressure bearing down on this side, plus you've got this much pressure from the mercury. So you need to add both of these together. So 24.3 torr is, well, the answer is in torr. Right? The answer is in torr, so we don't have to change that. What we do have to change is this one. 1.23 torr, atmospheres, excuse me, atmospheres is how many torr? This is a dimensional analysis problem. 760 torr per atmosphere. So 760 times 1.23 is 934.8. Then we add 24.3, and we get 1959, 959.1. We'll round it off. 959 right here. All right. 20. Consider a gas in a 1 liter bulb at standard temperature and pressure. Okay, so we got 1 liter, 1.0 liter volume at standard temperature and pressure. So for a gas, standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. This is volume, this is pressure, and temperature there. Okay. Connected by a valve to another bulb that's evacuated. Right. So it's connected to another bulb through a valve, and I'm not sure how big this one is yet. Let's see if it says. Answer the following concerning what occurs when the valve between the two bulbs is open. What's true about the value of delta H? Okay, so if we open that valve, what happens to delta H? Delta H is an expression of heat transfer. Was any heat transferred? No, it's got the same amount of heat it had to start with. It may be a different temperature after this gas expands into that space, right? Based on Charles' law. But the amount of heat transferred is 0. There was no heat transferred whatsoever in order for that to happen. Okay. All right, 21. In which group do all the elements have the same number of valence electrons? Okay. You need your periodic table again. Elements with the same valence electrons will be in the same group. So that's what you're looking for. Phosphorus, sulfur, chlorine. They're in the same period, but not in the same group. Right? So A is not going to work. Silver, cadmium, and argon. Okay. Silver and cadmium are metals. Argon is a noble gas. We don't even have to look at the table for that one. Sodium, calcium, barium. All right. Sodium is an alkali metal. It's in the first group. Barium and calcium are alkaline earths. They're in the second group. So that one doesn't work either. How about D? Phosphorus, arsenic, selenium. Phosphorus is in the pnictogens. Phosphorus is in the pnictogens. Selenium, though, is in the chalcogens. So it's out right now. Arsenic and phosphorus are in the same group, but selenium's not. So they're all wrong. None of those. They do not have the same number of valence electrons. None of those in those groups. All right. The ground state electron configuration of selenium. All right. Now, you can do this two ways. The exam will have that. Let's see here. I'll find it.
somewhere. Have that diagonal diagram. Here it is. This diagonal diagram shows you how to fill the orbitals. The other way, in fact, the way I would prefer, is to go to the periodic table. Okay, and notice where selenium is. All right, selenium has 34 protons, which means the neutral atom has 34 electrons. But notice the answers. The answers go back, this is the abbreviated shorthand. They go back to the nearest, go backwards across the table until you wrap around and find the nearest noble gas. So if we go from selenium and go backwards across here to potassium and then wrap back up to period number 3, we get to argon with 18 electrons. So argon with 18 electrons is where we can start. Now where do we go? Well, argon, we wrap down to the 4th period. Now we're in 4s. And we got to fill 4s, 4s2. Then we get to the transition metals. Remember, when you go into the transition metals from 4s, you go down to 3d. So 3d, and we go all the way across. 10 electrons. Okay. Now we're at gallium. We're into 4p. So 4p, and we're headed for selenium. So how many electrons are in the 4p orbital? Well, gallium is 1, germanium is 2, arsenic is 3, selenium is 4. 4p, 4. That's your configuration, and that is A. Okay. It's so much easier to write the electronic configuration with a periodic table. Uh, 23. I have to scroll this one. Okay. Which of the following bonds would be the most polar without being considered ionic? Okay, let me write all of them up here. I think that's probably best in this case. C, D, E. Okay, so we got a bond here. And we're not saying that these are compounds. We're just focusing on the bond itself. Oxygen, oxygen, silicon, oxygen, nitrogen, oxygen. Okay, so let's work the problem without being considered ionic. So which one would be ionic? Ionic bonds form between metals and nonmetals. Metal, non-metal. Can't be that one. That's ionic. How about the rest of them? Okay, the rest of them, according to our periodic table, the rest are non-metal to non-metal. So now we can look at their relative positions to one another in the periodic table, and we're actually comparing qualitatively the electronegativities. So the one that would have the most polar would be the greatest distance. Most polar, greatest distance. Okay, that lets oxygen out, right? It's not going to be polar at all. Carbon and oxygen are 2 places. There's an element in between them. Okay. Silicon and oxygen are 1, 2, 3. They're 3 places with 2 elements in between them. And nitrogen and oxygen are neighbors. Right? So that won't work. This one is the best choice. D. Silicon oxygen bond would be the most polar without being ionic. All right, 23. Let's see. 24. Which of the following atoms cannot exceed the octet rule in a molecule? All right, there's a hint here. What orbitals are available? Right. If you're going to exceed the octet, remember the octet is based upon s orbitals and p orbitals. You can put a maximum of 2 in the s's and 6 in the p's. That equals 8. So if you have an element that has available to it d orbitals, which means it has to have the principal quantum number 3. If it has d orbitals, then it can exceed the octet. We're looking for the one that cannot exceed the octet. So you can look at it that way, or you can use the periodic table again. And notice that if the principal quantum number is 2, right here, is 2 across here, those elements cannot exceed the octet. There's no way. They can be less than, like boron is, but they cannot exceed the octet because they do not have d orbitals available. Right? So sulfur can, phosphorus can, iodine can, they all have d orbitals available. Nitrogen does not. Nitrogen does not have any d orbitals available, so that's your answer. Because it is in period 2. 45. And 26. Which of the following has a 0 dipole moment? Remember what it takes to determine whether or not a molecule has a dipole moment. You've got to have 1, polar bonds. If there are no polar bonds, then there's no dipole moment. You can stop there. But if there are polar bonds, then you need to know the molecular geometry. Okay, so we've drawn these so many times. Some of them we won't even have to stop to do the Lewis dot structure and then use VSEPR. Right, you do Lewis first. And then you do VSEPR to find the electronic geometry. And then you go to molecular geometry. Okay, so A, we know ammonia is like this. Hydrogen here, hydrogen in the back, hydrogen there. Right, so they go like that. And then there's this. So that one has a dipole moment like that. How about NO2? Well, let's do this one. Valence electrons. So nitrogen has 5 valence electrons. Oxygen has 6 times 2, so that's 12 plus 5 is 17. 17 electrons. Nitrogen, oxygen, oxygen, 2, 4. That means we have 13 left over. 2, 4, 6, 8, 10, 12. So we have 1 left over. It has to go on the nitrogen. So that means it's going to be 1, 2, 3 trigonal planar. Right? And oxygen is more electronegative. So it's going to look like this and it's going to have a dipole moment like that. So this one has a dipole. A has a dipole, B has a dipole. How about C? PF5. PF5. Phosphorus has 5 electrons, and fluorine is a halogen, so it has 7 times 5. So it's 8 times 5 is 40. 40 electrons. So we put P here. 1, 2, 3, 4, 5. We need 5 fluorines. All right, so that's 2, 4, 6, 8, 10, 30, 2, 4, 6. 6 electrons around each fluorine means 5 times 6 is 30. We've used them all up. So this one is a symmetrical molecule, which is trigonal bipyramid. Phosphorus in the middle, and we have like that. And then we have fluorine down here and a fluorine up there. Right? That is completely symmetrical with the same bonds all around. So this one is nonpolar. Okay, and we found our answer. If we draw out the structures of the rest of them, SO2, which would look like water, and HCN, which is a linear molecule, but it has unequal polar bonds opposite one another. So nitrogen wins and you get a polar molecule. So this is the only one that's nonpolar out of all those in that question. All right, 26. The hybridization of the central atom of XeF5 plus. XeF5 plus. Okay. So we have 8 electrons here. We have 7 for each of the fluorines times 5, but we lost 1. So it's 6 times 42. 42 electrons. Okay, so we draw our molecule, and we have 5 in there, which means, well, we just draw them like this for now because we don't know the geometry. We've got a place for each of the fluorines, and that's 10, which is 32, and then we can put 6 around each one of these. So 5 times 6 is 30. We have 2 electrons left over. Okay. That means 1, 2, 3, 4, 5, 6. 6 pair or 6 effective pairs or 6 groups means what? Octahedron. And what hybridization on this atom will give you equivalent atomic orbitals, hybrid atomic orbitals, to make this symmetrical. D2, sp3, 3, 4, 5, 6. D2, sp3. That's E. Let's see here. Yeah, there we go. 27. Which molecules have p orbitals that share an electron pair to create pi bonding? All right. Remember how we wrote organic molecules? Anywhere a line meets is a carbon, right? We just don't write the carbons in there. And we don't write the hydrogens in either. So if we say this one is C6, H6, that means each one of these has a hydrogen on it. And this particular model, benzene, has 3 double bonds. So what do we know about those double bonds? We know about a double bond that this bond has to be a sigma. Then you can have a pi. You can never have a pi without first having a sigma. A sigma is on axis, pi's are off axis. You can have 2 pi's, but you can only have 1 sigma. So, how many of these molecules share an electron pair to create a pi bond? Well, if you just look at the structure, each one of them has at least 1 pi bond. So all of them form pi bonds. This one forms 3, that one makes 2, and this one makes 1. So the answer is D, all of the above. $28. Okay. My answer is covering up a little bit of one of them. Let's see if we can figure this one out. 28. A species has the following molecular orbital, MO, molecular orbital configuration. So let's say we have a sigma 1s with 2. We have a sigma star 1s with 2. We have a sigma 2s with 2. We have a sigma star 2s with 2. We have a sigma 2p with 2. And oh, something's got chopped off. Oh, it wrapped around right here. That's the problem. So this one is a pi 2p with only 2 electrons. Okay. So how do we tell if it's paramagnetic, drawn into a magnetic field, or diamagnetic, repelled by a magnetic field? Paramagnetics have unpaired electrons. Diamagnetics have all paired electrons. So you can only have 2 here, so those are paired, right? We would write them like that. Each one of these are paired. How about this one? Right. Hund's rule says these 2 pi orbitals, molecular orbitals, you have to put one unpaired and another unpaired in there before you can start pairing them up. They only got 2. So this one is paramagnetic. But why is it paramagnetic? It's paramagnetic because it has 2 unpaired electrons. That's why B is the answer. All right, 29. I don't think we can get that one on there. If I can read the question. Which of the following? I'm reading between the lines here, but behind the cover. Which of the following has the strongest bond or the shortest bond? The strongest bond or the shortest bond, which are synonymous, is the one with the highest bond order. The highest bond order. So in order to tell which one of these has the highest bond order, you've got to draw the molecular orbital structure and then calculate the bond order. But it's really not that bad, because what we really need to do is just take the neutral atom. Notice that these are ions of that dinitrogen. So we just do dinitrogen and then reason it from there. Okay, so for the neutral dinitrogen, we have, and we're just going to do the valence. We're not going to do the chord. Sigma 2s, sigma star 2s, pi 2p. Yeah, this one exhibits sp mixing. So the pi comes first and then the sigma. Okay, And then we get to the pi star. And I think that's all we're going to need. Because nitrogen has 5 valence electrons each, which is 10. We need 10 electrons placed. 2, 4, 6, 8, 10. Okay? So we didn't even use this one for dinitrogen, but we're going to leave it up there because if we're going to make a negative ion, we're going to have to start putting electrons in that orbital. So I'm going to leave it up there. Okay. So what's the bond order for this one? Bond order equals 2 plus 4 is 6, 7, 8 minus 2. Anti-bonding, bonding minus anti-bonding divided by 2, which is 3. Okay, now if we go to N2 minus, where does that extra electron go? It goes right here, which increases this to 3 and decreases that to 2.5. So this is for B. How about C? Let's do it over here. This is B. This is A. So this one is bond order 2.5. What if we add 2 electrons? Well, they both have to go in here, and we decrease this one by another half. How about D? D, we're actually adding an electron, subtracting an electron. So if we subtract an electron, it has to come off of a bonding orbital, which decreases that value again to 2.5. And then E, we're going to take away 2 electrons. Right? So the highest bond order, the strongest bond, the shortest bond is dinitrogen, the neutral molecule. That's 29. And maybe I got time for one more. Let me see, where's that going to put us? 29. And we've got a total of 49. The later ones have multiple parts, so we're about halfway. That's good. We can finish it up on Thursday. Let me do one more. Third. Number 30. That's good. The color changes. Equal masses in grams of hydrogen gas and oxygen gas. Equal masses of hydrogen gas and oxygen gas are reacted to form water. So equal masses. It doesn't say how much. It just says equal masses. So this is X grams. This is X grams. Exactly the same. Which substance is limiting? Okay. We need a balanced equation first. So 2 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens. Now we need 4 hydrogens. There we go. Now we're balanced. So if we have equal masses here, what's the ratio of those masses to one another? Remember, if we're going to find limiting reactants, we've got to know how many moles. Right? But they're both equal, so we don't actually have to know the value in order to find out what's the molar ratio of these two. Well, the molar ratio, the stoichiometric ratio, is 2 hydrogens for every 1 oxygen. So what would it be if we have X grams of hydrogen, and we have hydrogen, 2.02 grams per mole. And then we have oxygen. We're going to have the ratio of this one to that one, this one to that one. We're going to find out if it's stoichiometric. Oxygen is, for every mole, we have 32 grams. Okay? So the ratio, grams cancel. And now we have those grams cancel. We have 32 on top of 2, roughly, which is 16 to 1. So 16 moles of hydrogen to 1 mole of oxygen. In this case, if the masses are equal, so that means hydrogen is in excess, way excess, right? 2 to 1 is stoichiometric. We've got 16 to 1. Just missed that. Okay. So that means the limiting one is oxygen. Okay. All right. So that's 30. And we'll pick it up on Thursday with thermochemistry, number 31.